afternoon, everybody. Can you hear me now? Oh, yes, you can. Hopefully. Thanks very much for coming back in good time. Just one small admin point. The tours for SSTL tonight, the list isn't full. There's accounts for about 3 or 4 more people if you want to go. But please sign up as soon as this session is finished. I'd now like to introduce Eric Bertels, who works for ISIS, and he doesn't work for the terrorist group.
It's AIS nowadays, right?
It's AIS,
yeah.
The BBC's not allowed, I forget what they're now calling it, but something different apparently. For those of you who don't know, AMSAT-UK and ISIS have a very special relationship in so much that it's really ISIS who built or assembled FunCube and also handled the launch very excellently, in my view. I don't know whether you had much to do with FunCube or not really.
No, that was just before my time.
Oh, just before your time. Okay.
Just.
Anyway, Eric's going to give us, it was Wood who did a lot of the work for ISIS, but Eric's going to tell us a bit more about ISIS, what they do, and how they can help you into space.
Yeah.
Is that fair?
Well, yes.
Over to you.
Right. Thank you very much for the introduction, yeah. So, as mentioned, I'm Erik Bertels. I'm a systems engineer at ISIS. For those of you who don't know ISIS, we basically manufacture, sell, produce subsystems and complete satellites, mainly in the CubeSat sector. You know, we're branching out a little bit. We're going a bit larger sometimes. But today, I don't want to talk about future developments or the company, but I actually want to talk about what we've done. Of course, Graham already showed you a few nice graphs. I'd like to add to that as well. So mostly in-flight results from the systems we have in space. So, that worked well. Right, so currently we have several satellites carrying ISIS equipment. These are sort of in the order they were launched. So the Orbit Sail recently launched on the DMC-3 launch. Had a few avionic subsystems. And then the QB50 precursors, already introduced a little bit. TRITON-1 and FunCube on the same launch. So today I'll be talking about the 2 ISIS-operated satellites, which are TRITON-1 and QB50 Precursor 1 and 2. So actually 3 ISIS-operated satellites. So let's start with TRITON-1, as that's the oldest one, as long in space as FunCube is. So why did we start to build TRITON-1? Well, TRITON-1 is a mission which was supposed to do AIS. For those of you not in the know, that's basically ship tracking. It's a growing market. We identified it. We wanted to get into it. So what did we do? We started to design an AIS payload, which would have to fit in a CubeSat, basically. So it took quite a while. It's not easy. So we at least started thinking about, so how would this work on a CubeSat? Well, let's keep it as simple as possible. So we have a satellite in orbit. It should detect ships. It stores the ships it detects. Then you download them when you're in view of a ground station. You process the data a little bit, and then you go on and distribute the data. So you need the receiver. So this is what the receiver eventually ended up looking like. Few boards, fits in a 1U stack, lots of RF boards, interface boards, power supplies. Was quite an achievement to get that in such a small volume. So the complete satellite, as I mentioned, a 3U, tried to go as redundant as possible. So 2 radios at the point, a bit of attitude control in the form of magnetorquers. At that point still the nanomined IOBC, EPS. If you put solar cells on it, it looks a bit like this. This is a satellite just before it gets to be sent off into space. And it looks a little bit better when you put solar panels on. Still, we needed a ground station as well, so that had to be built, set up, making the complete infrastructure work. So this is the ground station in Delft, actually. A few Yagi antennas. You can see TU Delft in the background. Not the nicest of weather. So as I mentioned, with solar panels ready for launch, so the animation was shown already. So one of the 3U CubeSats you saw from the NEPRO launch, I was actually Triton. So always a very exciting time. You might recognize someone here. This was our previous operations room, so everyone was sitting really tense. Will we hear it? And then, of course, we heard it, so we were really happy. We got a few telemetry channels back. As you can see, it was a bit cold. The antennas are at -10, -20 even. But other than that, everything seemed to work pretty well. Power going in, the total power going out, not that much different than what we expected. So everything seemed to be in order. We started collecting some more data to see if everything went fine. So we started collecting temperatures and we noticed it was a little bit cold. You can see that the external temperatures dropped to -20. Some of the other temperatures just around 0. So what you do, you try to increase the duty cycle a little bit. Now that had a side effect basically. Basically we deafened the satellite a little bit. Well, that's not what you want. That had to be solved, of course. So what do you do when you can't communicate with a satellite? You try to shout at it, because that's what my courses always taught me. Ground stations are easy. You can just put in a lot of power, and then you will be able to get contact with the satellite and be able to command it actually again. So a lot of people, not myself because I wasn't working there, drove up, brought our equipment over to the Dwingelo station, very large dish, and of course you weren't allowed to point right at the horizon because you might cook a few birds. But the first command we sent through that dish went in, everything worked perfectly fine. So, of course, issues you always find. Luckily, you have to know the right people to be able to solve them. So in the end, the mission was actually a success. So the red dots represent ships which were detected using the payload and then downloaded back to our ground station. So as you can see, it's quite a wide field of view and quite a lot of ships. I'm not quite sure on the statistics, but this was gathered in about 10-15 minutes of payload activation. So it proves that the concept actually works. Now, getting this picture wasn't really easy, even though we had the initial problems. We also had, during operations, quite a few issues, I'd say. Road to get there was pretty hard. We had a lot of interference, quite a lot. It was really hard sometimes to get the signal in the satellite or decode the satellite. We don't really know where it was coming from, but yeah, a lot of interference, and that of course led to a lot of data link limitations. So the concept was proven to work. So in our regards, the mission was quite a success actually, but it took much longer than expected. Because it took much longer than expected, some of our operations guys had moved on. So this was a typical operation room at some point in the mission, which of course also added to quite some delays. So what can we say about this mission at least? Well, at least our first mission, well, we consider it a success. We learned quite a lot, which we also took for future missions. So, and despite some initial challenges, the satellite's still okay, so we're still gaining some flight heritage. Payload seems to be working. Platform, yeah, with the interference and everything, it's still quite hard, but we can sometimes work around it to have some regular operations. Well, as the proof of concept is now finished, it's sort of in idle mode, I'd say, right now. And it paves the way for some new platforms. Apply the lessons we've learned with regard to RF and everything to this. So that's what we did. We thought, well, we've built a few satellites. We've built this one satellite and it seemed to work. Let's go to the next one. And of course, the last conclusion is make sure that you have the right friends. Well, looking at this room, I think we found at least a few. So yeah, going on to the next mission actually. So the QB50 precursor mission came up. Well, if one satellite is not enough, let's build two. The development time for these two satellites was pretty rapid, I'd say. We started the project October 2013, and they were launched somewhere June 2014. So that's quite a short development time, even though we had now quite the experience, of course. But yeah, we had to do it, we had to deliver it, 2 satellites. Well, in the end, we managed. They're still in orbit. They're still functioning, so it shows that it can be done. So the precursor mission's main objective was basically to de-risk the main QB50 mission. I'm not sure if you're all familiar with QB50. I think most of you are, but basically QB50 is a mission which is led by VKI, and it's a mission which has quite a lot of universities who will contribute a few satellites, 1, sometimes 2, and it will be deployed in a very low Earth orbit, and then we'll start measuring the atmosphere. Well, the altitude at which it will be, which this will be deployed, the main mission is about 300 kilometers, maybe a bit higher, but that means the satellites will deorbit in about 3 to 6 months. So troubleshooting is pretty much out of the question. Thus the precursor mission. When they came out of the deployer, they were actually pretty high. So they started out at 30 degrees per second, which was quite a lot. So that was also supposed to go back a little bit. So what has happened since? Well, for ISIS, a very big milestone actually. We uploaded a new version of flight software to both satellites, also to fix the reboot issues, to fix a few bugs we found. And actually that showed a significant improvement. So the lower part left, that was the initial start of the mission. You can see that we had about 5 resets per day, which was quite a lot. And then after the software upload, we went to about 0.8 per day. So quite a significant improvement. So definitely something we want to do a few more times in the future, probably. So with this, we could also get some nice graphs. Now I know you all like colorful graphs, so I put quite a few in. So these are the panel temperatures, exterior panel temperatures for the period of about a month. You can see that it's quite stable actually. It's in a sun-synchronous orbit around 600 kilometers. You can see that everything sort of stays between minus to plus 20 on the outside. So that's pretty nice. And if you zoom in a little bit more, then you can see the spin of the satellite really, really well. So you see here the periods, of course. So the satellite's supposed to spin around the orbit normal axis, so it's basically slowly tumbling around the orbit. That's what you can see here, because this one is really stable, while these are alternating a little bit. That's the default mode it's in. So even though you might not always trust your primary telemetry, you can always deduce it again a little bit. So internal temperatures, a bit the same. So this shows the onboard computer and the power amplifier. You can see it's a bit warmer, around 0 and 20. So that's sort of the really nice range you want to be in. So apparently our thermal design was a success. If you zoom in a little bit more, then you see a really nice curve, just completely what you expect, just lagging a little bit behind the eclipse times. A few flukes here and there, but well, we just ignore these. So yeah, same graph for the EPS. It's a bit colder. We're not really sure why. It's lower in the stack, so maybe that's why it's a little bit colder. but currently we're not really worried because it's been working that way for quite a while. And here you see that the frequency with which it's measured, the step is actually a bit larger. So if you zoom in a bit more, you can see this. So this data is more than pretty pictures. It also allowed us to validate a lot of our models. So the temperature and power models, we could correlate this with the data, which is for future missions, of course, really nice to have. So if you look at the power budget, I noticed that for the precursors and for the AMSAT payload activation, this is actually quite interesting. So we looked a little bit at the power budget. So what's shown here is the incoming power and the outgoing power. Well, the incoming power is really hard to see because it spikes a lot, especially when you have a month. So you see eclipse, sunlight, eclipse, sunlight. So if you smoothen that out a bit and take the average, then you get that the power generated is about 2 watts, which was expected, and maybe a bit on the low side. And the average power used is about 1.9 watts. So we have still 8% margin, which means that can be used when the amateur payload goes online. We can still reduce the average power used also a little bit by playing with some settings on the ADCS or on our own radio. So there's at least enough margin when you look at the complete satellite. So Graham also showed the eclipse. Well, we saw it as well. We're coming from the other side, so FunCube is actually going to the North Pole. No, going south. We're going north, so you actually see here the nice dip again. Which is, and we incidentally also downloaded the data real time, which is why you see the increase here. So a few more things could be done now that we had whole orbit capabilities. So we could calibrate the sensors on the ADCS unit a little bit better, so we could have a more stable satellite. So it was now still spinning at about 2 degrees per second, and we wanted to get it a little bit more in a proper orientation, that it was at a complete standstill. So we tried. So first we started by just outputting the angles. Well, here you can see the rates going really at that 2.2 range a little bit. It looks a little bit populated, but if you look at the rates, they're really low, and you see sort of from minus 180 to plus 180, and it's apparently also oscillating a little bit. So we could calibrate it a little bit more. So we went to pointing. So you first see the pitch angle, it's still rotating. Then we started a momentum wheel, which soaked up that additional momentum. And then you can actually see that it was somewhat stable, I'd say. If you take a good look, you see it's at about 50 degrees, so it was off pointing a little bit like this. Probably that will be a bit better once we calibrate the sensors a bit more, play around with the settings, so that's still ongoing right now. And yeah, also shout out to SSC, who's been providing quite a lot of analysis, and who've been supportive throughout the entire campaign, even though we have to go back and forth and try something else again, but we're confident that we're getting there. Well, there was one additional issue, which was that for some unknown reason, somehow the EPS switches off the power to the ADCS unit. That also resulted sometimes in a spontaneous spin-up. We're still not sure why, but when the power goes off, it starts slowly spinning up until it gets to 30 degrees per second again. So that also slowed down operations quite a bit. We're still not sure why. Well, next to the ADCS, we also have some science units on board. We're still a bit ongoing, so most of them, well, there are 2 of course, but they're now calibrated. We're actually getting some science results, so we're getting also to the end stages of the mission actually. In the meantime, we also tried the activation of the AMSAT-NL payload, or the FunCube 3, 4, I'm not sure which one it is actually right now. So on the left you see our telemetry beacon, it's just BPSK, and then here the transponder came online. So you see a nice dimple in the middle, but other than that, I think the activation was pretty successful. First time round we did it just during the pass, then a bit further away we activated for a full orbit. Unfortunately, the orbit, we have to turn it on. We have to have subsequent passes, so we can turn it off ourselves again. That meant not a lot of people could contribute because of the orbit and the footprint we had back then. On the other satellite, we had a AMSAT Francophone payload. That was also activated. We went right for a full orbit because of geographical differences. We had to have a little bit of margin. The passes didn't overlap really nice. And that was shown to work as well, just about when we were a year in space. So the conclusions, well, we didn't see the same issues as we had on TRITON-1, so whatever we did, that improved. Of course, we found new errors. We had quite a lot of feedback for the QB50 main mission, playing around with the ADCS to get everything stable, providing the data. It's really helped the QB50 team quite a lot. And we have at least some science data now, which is still being correlated and evaluated. But yeah, everything seems to be going really well with that mission. Oh yeah, that brings me to the end of the presentation. We have some questions.
Any questions? Any from the internet? Just like, could we go to the microphone?
Yeah.
Do you have a rough idea where it will be turned over to the Amazon community?
Yeah, I sort of expected that question, yeah.
That's why I
Being
asked
here, yeah. Well, so it depends a little bit on when the payload providers come back with their analysis, and unfortunately they haven't given us a real estimate yet. So I can't really give you a date yet, but I hope it will be relatively soon.
Okay.
It seems to be ramping down.
Personally.
Yeah.
Any other questions? Go from back.
Question from the internet. When will the amateur transponder be switched on?
Yeah, that was exactly the same question. Yeah. Yeah. Sorry?
How about on Triton?
On Triton? Yeah, I'd have to talk. I'm not that much involved with Triton, unfortunately, so I can't really say something about that either. I do know that because of all the interference and everything, commanding is really hard. So I'm not really sure what we'll do with that, but you'll be definitely notified, of course.
Any other questions? Eric, thank you very much indeed for a very interesting talk.